Good afternoon, everyone. So as not to waste time, I'd like to start and welcome you all. Thank you for joining today's session. It's the first of its kind for the Groundwater Division for the Western Cape. I'd like to give a special thanks and welcome to some of the members from other parts of the country. We have the pleasure of having our national chairperson with us today, Mr. Farnes Fourie. Thank you for joining us. Just a few rules or a few important pointers. For those who are new to Zoom, please mute your mics, or the co-host will be muting your mic so that we minimize interferences. People are new to Groundwater Division, or if this is your first ever, you are welcome to join by the Groundwater Division. So today we have Ms. Lasher-Scheepers from City of Cape Town, a registered PhD student at UWC, and she will be talking to us about fate and transport of microplastics in groundwater. I will now hand over to Candice.
Hi, good afternoon, everyone, and thanks for joining. Okay, so I'll just get into it. Can you hear me, Sumaya? Everything's fine? Okay. Please forgive me. I'm very nervous. I haven't spoken to a lot of people in a long time. It's been locked down for a few months now. And I also got out of my pajamas today for you guys. So yay, here we go. So the title, Fate and Transport of Microplastics in Groundwater. I'll just give you an overview of the literature review that I've done so far, and a little bit of progress to date in terms of the project and what we've done so far. Yeah. So I'll go through the outline quickly. So we'll just go through research objectives and questions. I'll chat about what microplastics are, where we find them, how they travel, and then some of the properties like degradation, transportation, and then the fate. We'll discuss a short, brief discussion on treatment of microplastics, and then potential risks, and then we'll go into the research design. So the research objectives and questions. So the main objective of the study is to determine whether microplastics present in groundwater will have a negative impact on an aquifer system. So I'll use two case studies. I'm using the Cape Flats Aquifer, and I'm using the Atlantis Aquifer. And so the following question, so we all know that with the City of Cape Town is developing two managed aquifer recharge schemes. One is already developed, operating for almost 40 years now. The other one is the new one, which is your Atlantis managed aquifer recharge scheme. So the study will definitely benefit the city in understanding and determining whether there will be an impact, and then we know how to manage and control the problem. So the following research questions therefore form the basis of the study. Will microplastics move through the aquifers? What is the fate of microplastics in the Cape Flats Aquifer and in the Atlantis Aquifer? Will microplastics influence the transport of hydrophobic toxins in an aquifer? And what is the best way to manage and or limit impact of microplastic contamination in these aquifers? So we just have a look at a scale What are microplastics? So we know that microplastics are synthetic polymers like plastics or elastomers. Plastics, we're all familiar with them. So we've got HDPE, LDPE, polyethylene, um, uh, PET. I'm not going to say these names because they're very tongue twisty. We've got PVC. As a hydrogeologist, we know PVC. We use it all the time in casings of well points and so forth. Um, and we know HDPE as well. And then a lot of them, we see it every day. Like, look around you at this very moment. Somewhere you are touching plastic, or it's somewhere around you. There's just no running away from plastic. So it's all over. Um, and then plastics have additives in them. Why do they include additives in plastic? So it's either to make it flame resistant, so you'll have a flame retardant in. You have long chains of polymers, so you've got cross-linking additives which join the chains. You've got antioxidants so that they don't break down um, in certain environments. You've got plasticizers, you've got stabilizers, so it can either make it flexible, it can make it hard. So that's why that's why they include additives to plastics. And then, so basically, the overall topic is plastic, but then it's broken down into microplastics. So microplastics, according to a lot of research, and is anything between 5 millimeters and 0.001 millimeter, which is 1 micrometer. The scale on the side just gives you some kind of idea. So here we've got from 1 millimeter to 2.5 centimeters. Microplastic starts at the 5 millimeters. Um, and we've just got a comparison to ants. And then we've got your micro sizes, which is, you've got a comparison to dust mites. And then we've got nano sizes, which is your bacteria, your viruses, your DNA. So we get really, really small particles. This research will focus on microplastics. Not sure we'll do nanoplastics. It is, I mean, detecting it is a problem, or at least it's still something that that the researchers are working on. So for the study, we'll work on microplastics. And then plastics itself have different densities. So you've got like a really, really light plastic. So you've got your 0.06 density, which is natural rubbers. And then you've got a density of 2.2, which is your polytetrafluoroethylene. That they use that to coat pans. So you've got also known as Teflon. So plastics come in different types. It has different densities. Your microplastic itself comes in different shapes, and then it also has different colors. And I've mentioned this, that anything smaller than 1 micrometer is then referred to as nanoplastics. So we've got I've had a look at different types, shapes of microplastics. And so we can see we've got fibers, but then fibers are also classified. You've got your clean cut edges of fiber, and then you've got your frayed edges of fiber. Then you've got your fiber bundles, and research shows that fiber bundles almost really like untangle, so they stay in that knot form. Then you've got your fragments, which occur in foam, as foam, and sorry. You've got fragments, so D, E, and F. You've got your rigid and your irregular fragments. And then you've got spheres, or known as beads. They're round and smooth. We've got pellets, also round and smooth, but they can also come in cylinder shapes. And then you've got your foams, which are flat, thin, and malleable. And then you've got your foam, which is soft and compressible. I'm sure all of you are looking at this now and you can somewhat identify where specific shapes come from or what type of plastics it's broken down from. But then if you go further into microplastics, you will pick up that there are two sources. So you've got your primary source of microplastic and you've got your secondary source of microplastics. So your primary source of microplastics is any plastic that is made with the intention to be really, really tiny. And I've got two images there of, you'll see over here, it's like some gel with very small polyethylene micro beads in them. That is, you'll find them in face washes, exfoliating scrubs. So that's plastic, it's micro beads that they add in your cosmetics. And it's made in that form, it's made to be small. And then you've also got your glitter, and if you're a parent, you know that glitter sticks for a very long time. It's not fun. So glitter is made in its microform as well. And then you've got pellets. So pellets are made, they make it small. I showed you a round pellet, and then you've got your cylinder pellets. They use that and they melt it to manufacture other plastic products. And then we've got secondary microplastics. Secondary microplastics are larger plastics. They degrade from larger plastics, so they break down from larger plastics. And I've also got examples on the side, so you can see plastic litter. You can see synthetic materials like your synthetic grass. A lot of people are putting in synthetic grass during the drought. And then you've got your rubber from tires, and you've also got synthetic fibers, which are we've seen in your clothing items. So a lot of the PET plastic bottles, they recycle, and they make like a micro fleece jackets, the K-way micro fleece jacket, and all of them, they made from recycled plastic. So in your washing machine, obviously you now have all your clothing items, and as it's washing, you've got some microfibers that they refer. I've indicated that microfibers will break down and be discharged through your washing machine water. Some studies show, a study by Brown et al. Shows that 1,900 microplastics, microfibers, can be discharged by one synthetic item in one wash. So that's 1,900 microfibers by one item in one wash. Just stop for a moment, think of how many times you do washing, think of how many clothing items is in that washing machine, and how many people we have living in the city, and we're all discharging, and it all goes to our treatment plants. Again, your micro beads, in your cosmetics, we wash our faces, it discharges to our water treatment plants. The micro beads, they say you can expect between 4,500 and 94,000 particles can be released during a single use of cosmetic products. So there's quite a lot of microfiber beads, in there. And then if you look at this diagram, we're looking at sources and we're looking at types of plastics, which kind of also tells me where it's coming from. So if I'm finding a lot of microfibers, I kind of start to think, okay, this might be more treated water or discharge coming from a treatment plant. If I'm seeing a lot of particles, fine rubber particles, maybe it's coming from stormwater runoff because of roads and so forth. So it kind of gives me some idea of the distribution pathways. So looking at another study, this diagram is taken from the study, but I've added a few extra arrows in. So we know that there could be potential distribution pathways from the atmosphere directly to groundwater. There's also groundwater, if there's microplastics in the groundwater and we're using it for agriculture, so there's a direct source. The diagram also excludes direct links between your domestic industry and groundwater. And then the diagram also excludes a direct link between your water treatment plant and groundwater. We know with the drought, and it's been a practice for years already, but with water scarcity, we're now seeing a lot of municipalities moving into managed aquifer recharge, either with treated wastewater or with stormwater. So we've added those links in as well. So just looking at occurrence of microplastics, I won't go into a lot of detail, but studies have come about for years now in the marine environment. So some of the first studies where the term microplastics was introduced in around the 1980s by Peter Ryan and his team. They work on in the marine environment. And so you can see there are quite a lot of studies that's been done in water in the marine environment. And then more so, we start to pick up on freshwater environments. So we've seen all around the world, they've done microplastic sampling in rivers, estuaries, wetlands. There's evidence to show that it's present in these freshwater environments. And then I've also added in, they've done sampling of tap water around the world, and they found microplastics in the tap water around the world. Treated water, there's microplastics, and the raw effluent, we know there's microplastics. But what about groundwater? So the study is about groundwater. So the literature that I found on groundwater, I could only find 2 articles. And so that's a little red line that I've added in. It's not to scale, but it just shows that there's very little information on groundwater and microplastics. So the 2 studies, the one done on a caustic aquifer, in fact, both of them, and the one is in the USA. Of the 17 sites that they sampled, they found microplastics in 16 of them. With concentrations, the mean concentration is 6.4 particles per liter, and the maximum of 15.2 particles per liter. I should mention that with the studies, there's often, because there's no standardized protocol on how to do it, it's a new thing. So a lot of the studies will report in an area, and then others will report particles per liter. So it's difficult to do a comparison between the studies because their units are not the same. And then they found that microfibers in the study was smaller than 1.5 millimeters. They identified 4 of the samples as being polyethylene, and the rest were basically destroyed during the identification process. And then the study also highlighted that fractured aquifers are also vulnerable to microplastic contamination. And then we've got a local study done by WRC in Potchefstroom. It's a WRC study, sorry, done in Potchefstroom, where they sampled 4 boils and they found microplastics. They divided it into particles and fibers. And I assume particles is any of the other fragments and pellets and so forth. They found that with the particles, 80% of the particles in the groundwater were between 0.02 and 0.3 millimeters, and then 20% is slightly higher, you can see from the graph, whereas with the fibers, they appear across all size ranges, and of with a maximum above greater than 1.5 millimeters. So now we know that they found microplastics in groundwater. So now that kind of gave me some more motivation to go further and research a little bit more. So I looked at degradation. So you've got your plastic, your bigger plastics. How do they become microplastics? So we've got degradation, and the degradation process is split into 2. The degradation process is split into 2 processes. So we've got abiotic processes and there's biotic processes. The abiotic processes are divided into physical and chemical processes. And the physical processes I've indicated, we've got abrasive forces, you've got your heating and cooling that can cause a particle to break down, freezing, thawing, wetting and drying as well. And then with the chemical processes, you've got photodegradation by UV light, oxidation, and or hydrolysis. And then you've also got your biotic processes, which relies on microbials to break down the plastics. Now, some plastics have additives in and make them kind of resistant to oxidation and so forth, and then it makes them stronger. They don't break down. However, if you look at the degradation processes, the biotic process in some instance rely on the abiotic process first. So it would go through the whole abiotic process and it would break down into smaller pieces, and then it becomes available for microbes to degrade even further. But in some instances, it's not even available for microbes to degrade because of the composition of it. So we looked at degradation further, and studies have showed that the degradation rate is the differential mass per unit time. So that's how they determine degradation rate. Degradation, so what does it do to the plastic? It alters the size, it alters the total surface area, the mass, the surface roughness, the molecular weight, and the charge of that plastic. So the diagram just shows total surface area, an example of total surface area. So if we have a particle that's 1 centimeter by 1 centimeter, the total surface area is 6 centimeters squared. However, if this particle now breaks down, degrades into smaller particles of 0.5 centimeters, the total surface area of that whole particle, of all the particles that now made up that one particle, is 12 centimeters squared. But if you break it down further, the total surface area becomes 17 centimeters squared. So we can see that the volume remains the same, but the total surface area increases. Now, why is this important? So the impact of degradation, according to studies, have showed that the decrease in the plastic size will result in faster degradation due to higher reactivities. It also, as it degrades, it releases ketone groups and ester groups, which are additives in the plastics, and then it alters the surface roughness and it changes the charge of that particle, which now allows adsorption to occur. It changes the molecular weight of a polymer, so it's chemically modified from a polymer to an oligomer to a monomer. So it's now no longer a polymer. So what are we working with? And then studies indicate that in some environments, the degradation process is really slow. So if it's slow, it means that there is a constant source of microplastics. So it's a long-term threat to the environment. So it's there and it's slowly degrading, but it's continuously providing that source of microplastics to wherever. So this is just an example of different types of plastics. We can see PET, HDPE, PVC, and then the different colors indicate different environments. So L represents landfills and compost soils. M is the marine environment. B is the biological environment. S is in sunlight. So we can see with fillers, without fillers, there are different degradation rates for different plastics in different environments. So we're working with something that's really complex and changes. Really, the change is very sensitive to environments and types of plastics. So now that we know degradation, we know how the plastic particle was formed or processes that could form the particles. We look at transportation. And so I found transportation processes. This is just an example of transportation processes in rivers. So you've got your dense and your less dense, which would make it buoyant or non-buoyant particles. So your non-buoyant particles, it comes into the river and it can settle immediately. So you've got number one, which refers to your turbulent transport. You've got number two, which refers to settling. You've got number three, which refers to your aggregation process. And then number two again, because now it makes it even heavier, it can settle further. You've got number four, biofouling, also leading to settling. And then you've got 5, which is resuspension, and you've got 6, which is burial. So it can be embedded into the sands in the river systems, but again, it can resurface basically, and then undergo that process again. Sorry, that's non-buoyant, and then you've got your buoyant ones. So you've got your turbulent process, but obviously it's buoyant, so it's not going to settle. So it needs other particles to attach to it to make it heavier, and then it settles down. And then you've got biofouling as well, and then you've got your burial, and you've got your resuspension again. But also noting that these are obviously flowing rivers, but you've got rivers that dry up in some seasons. So as the level lowers in your river, you're obviously going to have settling of those microplastic particles into the beds of the rivers. Okay, so now we look at transport in groundwater. And basically, I couldn't find anything about transporting groundwater. I did find an article that refers to earthworms creating preferential pathways, and the microplastics could attach to the earthworm, and the earthworm basically takes it lower down in the soil horizon. That's all I could find. And so it led to further studies. And it led to the study where they did an experiment on the fate of microplastics in soils. So the aim of the study is to determine if there was an impact of microplastics on the biophysical properties of the soil. And so what they did was they conducted like a garden irrigation experiment, and irrigated with water mixed with polyacrylic fibers and beads and polyester fibers, polyethylene fragments. But this was for a loamy sand soil. And then they measured certain properties, and they found that the bulk density was affected and the water holding capacity was affected. The functional relationship between the microbial activity and water stable aggregates were affected. They did not see any change in hydraulic conductivity, but the study highlights that again, they used specific types of plastics, specific sizes in a specific soil. So this, it doesn't imply that irrigation of a source with microplastics will not have a change on hydraulic conductivity. It's just in the specific environment. So it led to microsphere studies. So we know that microplastics are small particles, we know the sizes. So we looked at studies, colloidal studies or microsphere studies in groundwater, which are particles more in the lower range of microplastics to nanoplastics. And so there's been studies over the past few years where they used a fluorescent carboxylate modified microsphere, which is polystyrene or latex beads. And they use these as tracers in groundwater experiments to determine the transport model of bacteria. So they use the tracer with the bacteria, with another tracer, and they wanted to see if this specific microsphere could be used as a substitute or tracer which would resemble bacteria in groundwater. And so the study in 1986, they performed forced and natural gradient tracer tests using these microspheres, as well as bromide and chloride. The microspheres were uncharged, and some of them were negatively charged as well. And they found that the microspheres were moving in the aquifer, and there was visible retardation and attenuation as well. And the other traces, the bromide and chloride, the peaks came through faster, like several 8 to 9 days faster than the microspheres. The bacteria also came through faster than the microspheres. So we went further into microspheres because it seems as though there's some resemblance between the microplastic that they use, between microplastics and the microsphere that they use. And so we went further into these studies, and we found that the transport of these microspheres was controlled by the pore water velocity and the attachment or detachment to aquifer sediments. It led to, in some of the studies, they did column experiments, and they found that there was a decrease in hydraulic conductivity when they injected these microspheres into the columns. And then the column experiment also showed that the permeability of the porous media is reduced significantly when they just add like even a smallest amount of these microspheres into the experiment. They immediately noticed a change. And so they assumed that it was because of clogging at the pore throat. So this is just an image of the microsphere that was used, and there's an assumption that at the pore throat, the colloid will kind of clog that pore and then reduce that flow. And so it also, the clogging, I mean, in these studies is also referred to as straining in an aquifer. And then we looked at different chemical stresses, what could change or impact the movement of these microspheres. And it was found that if there's a decrease in the ionic strength of the water, then there is mobilization. So, and then there's also with an increase in the pH, increase in concentration of surfactants and the dissolved organic matter, all of these can mobilize the microsphere. The ionic strength plays a role in the clogging as well. So it is something that must be considered when you are doing managed aquifer recharge. So we get to one of the other questions. We have some hydrophobic toxins and they don't travel, they stay there. However, we are now thinking that if microplastics do have the ability to move in an aquifer, will it absorb and allow that toxin to move as well? So we found that colloid facilitated transport can lead to great migration distances of hydrophobic contaminants. So we know that these microspheres, contaminants do adsorb to the microsphere and it moves it. And then further studies on microplastics itself found that ecotoxins also may adsorb to the microplastic and resulting in transportation. That is specifically in the marine and surface open freshwater environments. The microplastics with a higher surface area ratio, higher surface area to volume ratio, have a higher adsorption capacity. So I showed you the diagram where you have a particle of 1 centimeter surface area, but if that particle breaks down, the surface area becomes bigger, and the more it breaks down, the bigger the surface area becomes. So if it has a bigger surface area, there's more areas for the toxin to adsorb to now. And then other properties of plastics influencing adsorption. So when a particle is, compounds are 0.0 charge, functional groups, and acid-base characters. So these factors are all changed in a plastic when they degrade. So obviously making it available for adsorption then. So we looked at different types of toxins, and this is taken from various studies. I'm not going to say these names, they are really big and really complicated to say, but we are all familiar with PCBs, PHs, we know them, heavy metals. It was found that they all adsorb to microplastics. And then there's also a study that shows that antibiotics and microbes also adsorb to microplastics. So just quickly looking at, I'm not going to go into treatment processes, but basically what was found is that the conventional treatment process is not capable of removing microplastics. And then there are a few studies which show that the membrane bioreactors have a potential to remove a large percentage, like most of the studies are between 95 and 99% of microplastics, but these are all still anything that's greater than 0.02 millimeters. So anything smaller than that, there's a potential that it's not going to be removed. So possibly your nanoplastics. And then in the studies, they showed that the common microplastics were microfibers and microbeads. And as I've indicated, your microfibers are coming from your synthetic um, clothing items, and then your microbeads coming from your cosmetics, and also some of your detergents like your dishwasher and your washing machine um, um, pods as well. So as I've mentioned, what about nanoplastics? It's the membrane bioreactors do not have the potential to remove that, and we haven't gone into this yet. And then it also raises question about how do we manage or dispose the sludge coming from the treatment process. And also another thing to consider is that sludge is now being looked at to reuse as fertilizer in the agricultural area. So definitely we need to consider microplastics because that can be a direct link to your groundwater. And then how do we control or manage the source of the water coming into the plant? These are some questions that obviously need to be answered because you've got washing machines, you've got your discharge from your facial products and stuff. So how do you control that coming into the treatment plants? So we looked at the potential risks and research needs. So we know that there's a change in the soil biophysical properties, which can lead to erosion or water holding capacity, or affect the water holding capacities. Movement of microplastic through the aquifer, that's a potential risk here. Potential clogging of an aquifer, and the potential risk of microplastics facilitating the movement of hydrophobic toxins in an aquifer. And then, as I've indicated to you previously, you have additives, which makes the plastic, you can mold it, you can make it hard, you can make it flame resistant. So these additives, they could leach during degradation. And we've also found that some studies show some of the additives that are used in your PET bottles or so forth are carcinogenic, and also they are endocrine disruptors. So the research design, after all of the research literature reviews that we've done, we're now looking at microplastics as a microsphere, and as we've seen in the microsphere studies, they do move, they do reduce hydraulic conductivity, and they do have the ability to clog. So we are going to be doing field sampling in the Cape Flats and the Atlantis Aquifer area, but we won't only focus on groundwater, obviously, because the source comes from above. So we'll do groundwater sampling, surface water sampling, storm water, treated wastewater, and final process water. We'll target areas that we think would have a higher potential of contributing, like your landfill sites, wastewater treatment, discharge points, and so forth. We are looking at a plastic-free sampling process and analysis, processing and analysis, which is really, really difficult because everything has plastic in. So with the sampling process, you have to look at your equipment. What equipment are you going to use? Does it contain plastic? Is this plastic that you would think would be in that environment? Do I now have to remove that plastic as something that I should also analyze for because it might be compromised by the equipment that I'm using? The clothing that you're wearing could have plastic fibers in them, so we are looking at getting pure cotton, PPE, and then there's also no protocol available for groundwater. There is some standard guide that everyone is using, and so we'll use that guide and adapt it. And then also there is a guide for the microsphere studies to sample, but from what I've seen, the equipment contains plastic as well. So again, we can't use that. And then we've got field experiments and we've got lab experiments. And we'll use the colloid transport model principle for these lab experiments. But we'll use microplastics. And then some of the challenges, again, a plastic-free lab and equipment. And then finding or at least getting a suitable size microplastic that we can use as a tracer. And then, sorry, FCM is the fluorescent carboxylate modified microspheres. They are really expensive because their purpose is actually they use it in the medical field. So you need very small concentrations which they would inject into your body to use as a tracer. However, these microspheres have been used in the groundwater environment doing experiments, but they are very expensive. And then how do we detect the microplastic in these experiments or during these experiments? So progress to date, we are going to be using a lab at UWC to analyze to detect microplastics. We've made some microplastics with PET material. And we also are exploiting the fluorescent properties of microplastics. So you can see in this image, the PET is quite dense. I think it's got a density of 1.2, so it's going to definitely sink in water. You can see the small fluorescent particles. These are some of the microfibers that we've made in the lab from using PET. And then we've also collected sand in the Cape Flats Aquifer, and we filtered them, and it's in preparation for the column experiments. And then we've sourced funding for the sampling. And then we are in the process of recruiting students. So if anyone's interested, please pop me an email. And then the city is also supporting me with the studies, and they've now formed a collaboration with the Netherlands. So there will be a living labs. It has formed one of the living labs topics, and it's done through the city of Cape Town as well. And then, sorry, I didn't put this in the outline, but just looking at plastic bans or controls that's required. So, some of the issues we know and we see it all the time is referring to the single-use plastic, which end up on the landfills and all over the city. And so there was a charge imposed in 2004 on plastic bags, but consumers just became used to paying that, and so the charge now means nothing. The plastic bag use has increased again, so it's either they need to increase the levy on that charge or do something else. And then there is the National Department of Environmental Affairs. They are busy looking at uh, uh, re-looking at the plastic bag legislation, um, and also including all the other single-use plastics like your straws and so forth. And then this is maybe just my opinion, but micro beads used in your cosmetics and detergents, my opinion that it should be banned. I'm not sure how they're going to manage that, but I would prefer it to be banned. And then we also look at biodegradable plastics, which is now picking up. The research is picking up in that. But I've also found that some studies show that they don't always decompose fully. And then also there's no standardized time scale for the degradation, in which the degradation occurs. And then we've got the synthetic textiles, which is your clothing items. We'll have to determine how to control this, and coming in from your domestic areas. Provincial Department of Environmental Affairs is working on a strategy and looking at the mismanagement of plastic. So hopefully whatever comes out from the study will also assist them in making decisions. And then, well, we can all do our bit by awareness, letting people know what the impacts of plastic are, just being aware yourself of what you're buying, what you're using. Is it necessary? Do I really need to buy that bottled water, or can I just take tap water? And that's coming from a City of Cape Town employee working in Park Water. So that is the end of my presentation. And I think, Sumaya, we can open up for questions. Please go easy.
Thank you, Candice, for that very informative presentation. We really enjoyed it.